Okay, hello everybody. This is my video tutorial on mirrors and optics ray diagrams. And I'm going to do this in Flash, which is kind of easy for me to draw some lines and ray diagrams. It's not ideal. It's not as easy as using paper and pencil for this, and ruler, right? Don't forget your ruler, which is hopefully what you guys are going to be doing, but we're going to make a go of it anyhow. All right, so what you can see here in the screen is a plane mirror here. There's a plane mirror. And these little lines at the back represent the back of the mirror, so the non-reflective part of the mirror. So something like this thing here, a little makeup container. This is not mine. I don't need makeup. As you can tell, I don't even know how to open this thing, which probably would have been a good idea. There we go. Okay, so little makeup mirror, and that's the mirror part. So there you go. Have a look at yourself. This is a typical plane mirror, and you can't look through the back. Well, there's the plastic here, but generally the back side of the mirror doesn't work. So that was not the greatest demo, but that's a plane mirror anyhow. So just like I've got here in the image, and this green arrow with the O represents the object. So imagine that's you, all right? You're wearing green, so you're green there. Green with envy, or green grass at home, or something like that. And imagine that you are standing in front of a plane mirror, and you are looking at yourself in the mirror. And well, how do you appear? What is the image like? So we're going to draw a ray diagram. This actually won't be so much of an actual ray diagram. It's how to locate the image in a plane mirror. So I'm going to come over here, and I'm going to choose a particular color that I want to use, and I want to go to the line tool here. And what you do is, if you've got sort of a diagram of this, you draw a line. You measure a line from usually the top of your object to the reflective surface of the plane mirror. So I'm just going to go like this. It's not going to be super accurate, but I'm going to draw a line. That's not what I want to do. I want to set this up first. All right. And now I'm going to draw my line, solid line right to the surface of the plane mirror. Now, I don't have measurements on here, but you'd use your ruler. Let's imagine that's 3 centimeters. What you then do is you draw behind the mirror the exact same distance. I'm just going to grab that. And you go behind the mirror 3 centimeters as well, if it was 3 centimeters. But because it's behind the mirror, and I don't know about you, but on planet Earth, light does not go through a solid medium. All right, light can travel through many different media, as we already know, or as you should know. It can travel through air. That's how you're seeing me. Well, yeah, it can travel through the internet. Okay, anyways, through the air, through water, through glass, through plastic, and stuff like that. But it doesn't travel through solids. All right, so it doesn't travel through the mirror. So what we do is we make this a dotted or a dashed line. Now I'm going to use dashes because it's a little bit easier to see. So I have got a line in front of the mirror, and I've got a line behind the mirror, the exact same distance. Now, I'm going to choose another point on my object. In this case, it's going to be the tail or the bottom of the arrow. And I'm going to measure the distance. Now, because I'm standing vertically in front of the mirror, and those are my feet down there, the bottom of that arrow is my feet, it's going to be the same distance to the mirror. All right, but I'm going to just go ahead and draw it. So I go ahead and I draw that line there, and you can barely see it, and you measure behind the mirror the same distance that it was in front. So you do something like this. What did I do there? Let's try that again. There we go. Same distance in front, and this is a dotted line. All right, so if you can see that, and I hope you can, what you will find if we go ahead and we try to draw the image, all right, I'll draw this as solid, and we'll draw it right about there, like that. And it's not that easy for me to draw the arrowhead in Flash, but I'm just going to do something like that. There's our image, okay? And normally we would label that as you know, image, whatever. Actually, if I move that over here, use my Epic pen over here, grab this in a white color, and say I for image, okay? Really messy eye because I'm using the mouse to do this, not my tablet. The image in a plane mirror is the same distance behind as it is in front, all right? So if you're standing in front of a mirror and you are 3 feet away from the mirror, your image is 3 feet behind the mirror, or you think it would be. It seems like it is. It's actually not, but all right. Anyways, solid line, dotted lines, Same distance behind the mirror as it is in front, in terms of the diagram anyhow. Okay, now, next thing is, actually move that out of the way. The next thing is the fact that the image is right side up. So is the object. So the object is right side up, so is the image. And it's helpful when you look in a mirror, right? You look in a mirror and you go, whoa, I'm right side up, I'm not upside down. That would not be overly helpful if you're trying to like shave. You'd be like shaving your feet instead of your beard or something like that if you have a beard or if you have feet. So right side up object, right side up image. That's referred to as the attitude. So normally we do something called the SALT characteristics, the size, attitude, location, and type. So the size of the image, same size as the object, all right? You're looking at yourself in a plane mirror and you are the same height. You're not shrunk, you're not a giant or anything, you are the same size. Attitude, you are right side up. The image is right side up. Now, if the object was upside down, if you were standing on your head, your image would be standing on its head as well, okay? Location is the fact that the image is the same distance behind the mirror as the object is in front of the mirror. Now, the type of image, this is the thing that gets people. This is called a virtual image. So what you're seeing here on the screen, this arrow over here on this side, over there, that is a virtual image. It's not really here. I mean, it can't be, can it? This is a solid mirror. This is light. Let's say you're glowing. Oh, you're glowing today. You look wonderful. I'm glowing, all right? Well, as the light comes from me and hits the mirror, it doesn't go through the solid mirror and then goes over there. I'm not seeing through the mirror, seeing myself over there. The light is actually bouncing off the mirror, coming back to my eye, and I see myself. This is called a virtual image. It's not a real image. It's not really there. It appears as if it's there. Now, one way that you can tell a virtual image in ray diagrams like this is if the image is formed by dotted lines or the intersection of dotted lines. And we'll see a bunch of that in a little bit. Okay, so let's carry on. That's the idea of a ray diagram. Now, it is possible that you will have questions on tests like this, where, what do I want to do? Let's just take this object and put it over here, and let's just tilt it a little bit, and let's just, ignore the other one here. So focus on this object and ignore that one for a second, okay? I mean, I could put this on another layer, I suppose, and hide this on one, but let's not bother to do that. Let's do another diagram. Same idea. Locate the image in a plane mirror. So what you do is you take your ruler, you put it on the top of the object, measure the distance right to the mirror using a solid line, draw that solid line, and then draw behind the mirror the same distance behind the mirror and make that one a dotted line like that. Okay, everything's cool. Front of the mirror again, from say the tip or another point. Now you could use this point, you could use another point. It really doesn't matter, but it's easy if you go to the tip, and we don't want to do that. I want to go from here and right to the mirror, solid line, measure behind the mirror, same distance, make this a dotted line. Okay, so these dotted lines represent the light from the tip of the arrow and the tail of the arrow. So let's go ahead and draw that image arrow now. Okay, and just join these up like that, and it's not going to be super easy for me to draw this again in Flash, but you get something like that. There's the image. Notice the image is tilted. So if you were standing back like this, looking at yourself in the mirror, so your image would be, you don't lean back and your image is like this. You lean back and your image is like that. Okay? So same distance behind the mirror, same size. Attitude, it's upright, it's not inverted. Location, behind the mirror. Type, virtual once again. So every time you look at yourself in a mirror, you can say, I'm not really there. All right, great. Let's now move on to something else that you were probably seeing Geez, I wish I didn't draw those in that position. Okay, no problem. There's my object. Okay, we're going to move over to some curved mirrors now. I'm going to hide that. And let's come over to this typical curved mirror. Now, the line that goes straight through the vertex, or the sort of middle point of a mirror, is called the principal axis. So I've gotten written down here PA for principal axis. And we are going to also look at F and C. Now F over here, let's see, let's go over here. F, that is called the focal point. And you may or may not know this from possibly doing ray box experiments, is if you shine a ray of light parallel to a curved mirror like this, and this is the concave side, all right, so this is important. If it's a concave mirror where it's like you're going into a cave, into a little opening, the ray will be focused or will pass the principal axis at the focal point. The distance between the vertex of the mirror, which is right here, and the focal point, that distance there, that is the focal length. So sometimes people kind of use them interchangeably. But anyways, that's the focal point. So if I, do a parallel ray, right there anywhere, it's going to go through the focal point. Or if I do one right there, parallel to the principal axis, it's going to go through the focal point. So concave mirrors are also referred to as converging mirrors because the rays of light converge at the focal point. All right, so that's the focal point. Now, C represents the center of curvature. If this was a circle, all right, C would be right in the center of that. Okay, it's not overly important for optics diagrams. We don't really use it very much except to say, hey, well, if my object is between C and F, well, where's my image? All right, but the focal point is important, and we'll use that in looking at some rules of drawing ray diagrams. So I'm going to move the object out here, all right? And let's do an experiment, and let's see where the image will be produced if the object is that distance out beyond C, all right? And by the way, C is twice the focal length. If the focal length here is the distance between the vertex and F, if that was 2 centimeters, then the distance between the vertex and C would be 4 centimeters, twice the focal length. Okay, so it's almost as if this is referred to as 2F. Okay, now I want to show you something. See if you recognize this object. That, a spoon, okay, typical spoon. This side here is the concave side, and this is the convex side. Now, next time you're eating your breakfast, whatever it might be, have a look at the concave side of a spoon and look at your face in that side. And note what your reflection looks like, the image, in other words. Let's see if we can figure it out here with a ray diagram. Okay, so let's do this. Let's draw a solid line from the top of this object, the arrowhead. Often arrowheads are used because they're quite easy, parallel to the principal axis, and hit the mirror. Now, this is a solid mirror. The light will not go through, so it's going to be reflected back. And because it's a converging mirror, the light is going to be reflected through the focal point. That's what these things do. So you use your ruler and pencil and you draw this line as parallel as you can to the principal axis to hit the mirror. And we're, of course, assuming this is the reflective side of it. I didn't draw those little dashes on the back like I did in the plane mirror. I just didn't want to bother because I want to do something with this back side soon and assume it's reflective. All right. Parallel to the principal axis, you then go from that point back through F. It go a good distance, all right? Now, your optics diagrams are not going to be perfect. They're not going to be exact, and neither will the ones that I'm doing here. So not every one of these diagrams may work perfectly. We may have to fudge it a little bit. Now, don't forget, however, that these are rays of light, and a proper optics diagram shows an incident ray, the ray coming from the object hitting the mirror, and draws arrowheads like this. All right, not referring to this arrowhead, but a ray, an arrowhead showing the direction of the light. And you only need one. Don't go drawing a whole bunch of these things like that, because that's just a complete mess. Oh yeah, I'm using Epic Pen. All right, so one of these things, it's going to be tough to draw them very nice. I may switch to just drawing them in Flash in a second. So, the professional tutorial here, isn't it? The ray hits the mirror parallel and goes through F, and so this is also a ray, and that's the reflected ray, all right? Incident ray and reflected ray. All right, now we move on. The next rule for drawing optics ray diagrams is a ray that goes through F and hits the mirror is reflected parallel. So parallel and through F and parallel. So let's draw that. From the same point, I'm going to draw a ray of light coming through this focal point, hitting the mirror as best I can, and then coming back parallel to the principal axis. Now, once again, these are incident rays, so you can put your arrow wherever you want. All right, so that's an incident ray there. This is a reflected ray there, and don't forget those arrowheads. They're very important. Where the rays intersect, right there, that is where the image is going to be produced. And so I'm going to draw the image now. Draw it in green right here, like this. It goes and it touches the principal axis, and this is the top of the arrowhead. Okay, I'll just try to draw it like that. The reason is that the light was coming from the top of the arrowhead when we drew these rays. So where the rays intersect, that is the top of the arrow. The arrow was sitting on the principal axis. It wasn't levitating in the sky. And so the bottom of the arrow, the tail of the arrow, must touch the principal axis. And that will give you the size of the arrow. You don't do this. All right, you don't just draw that much. You draw the whole thing. It's touching the principal axis here, so it's got to be touching right there. Now that is the image, and generally you'll be asked to, label the image as well. So you've got object and image. Now we need to look at the salt characteristics, the image characteristics. If this was you, and you're looking at yourself in a spoon, the concave side of a spoon, your image will be like this. So let's do salt, size, smaller. So when you look at yourself in the spoon, right here in the concave side, you will appear smaller if you are beyond the point called C, beyond the center curvature of that spoon. Now, if I look at my spoon and I see the curve, it's going to go like that, whatever. So the center of curvature is like somewhere in there. So as long as I'm out here, my image is going to be smaller than I really am. And I'm looking at myself right now and I'm going, I look small. I am small. There's no way I'm going to be the same size. Well, all right, anyways. Okay. Smaller, that's S. A, attitude. It is inverted. It's upside down. So when you look at yourself in the spoon, you will see, hey, I look upside down. This is unlike a plane mirror where you're standing right side up and your image is right side up. In the curved mirror, in this location, the image is inverted with respect to the object. Okay? Location. Now, there's a couple of different ways of doing this. The location is in front of the mirror. In a plane mirror, the location of the object is in front of the mirror and the image location is behind the mirror, all right? But in a curved mirror like this, at that position, the image is in front of the mirror. It's also between C and F, all right? That's its location. The type of image, this is a real image. And again, this is the area that a lot of students have trouble understanding real image versus virtual image. It is really there. And the way that you can tell, maybe the easiest way, is the fact that the image is formed by solid lines. All right, if it's formed by the intersection of solid lines, it is considered to be a real image, not a virtual image. All right, well let's try something here. Let's get rid of all of this stuff, including that, and let's move the object in between C and F, and let's see what happens. So you're coming closer to the spoon, closer to any curved mirror, and let's see what the image characteristics will be like. So we are going to draw a solid line parallel to the principal axis, hitting the curved mirror, reflecting through F. I'll just pull it down a certain distance like that, okay? Yeah, we'll go ahead and we'll add arrowheads, incident ray, reflected ray. All right, now we need to draw another line. Okay, now there are a few different lines or rays that you could draw, but it's easiest to go through F. Okay, try to get it right through that point, hit the mirror, and then come back parallel. All right, as best you can. Once again, this is an incident ray here. This is a reflected ray there. All we need is one. We're in great shape. Okay, we can now draw our image because we have an intersection of these two rays. Now, if you do another ray, let's say through C, hitting the mirror, we'll do that soon, it should hit at the same spot. But all we need is two rays. So this is where we're going to draw our image, and it's going to touch the principal axis right there. And because it came from the arrowhead where the rays intersect, that is the arrowhead. Excuse me. So that is the image. And as you can see, it is larger. So once again, if you look at yourself in the spoon, if you start to bring it in, the image starts getting bigger. So the image in this case is for size, S, salt, larger, attitude, inverted, location, in front of the mirror, beyond C or past C. The type, real. It is a real image formed by solid lines intersecting. Okay, very cool. Now, let's try another experiment. Let us move the object up here. Let's say the object was about halfway between the vertex of the mirror and the focal point. What would happen then? Well, let's find out. Same rules are going to apply. We're going to go from the top right here, parallel to the principal axis, and we are going to move backwards, reflecting through the focal point, just like that. We're going to draw in, if we can, our incident ray and our reflected ray arrowheads. Okay, now let's move on. We can't do a ray out this way through F. Like, let's say we're going to go through F in parallel. If we go down through F, it's not even going to hit the mirror. There is another rule. Parallel and through F and parallel, and also a ray that goes from the object and hits the mirror at 90 degrees exactly, bounces through C. Or another way you could say it is a ray that goes through C and through the top of our image, hits the mirror at 90 degrees. This ray, if it was coming out of the top of this arrow and hitting the mirror, it is actually hitting right at that spot at 90 degrees. It would bounce right back on itself and that kind of thing. And so to do this, this arrowhead is a little bit awkward. It's kind of like a ray's going in that way and it's going out that way, right back on itself. Now, if we were to extend these rays, let's say pull this out and trying to get the exact angle still, you'll note that these rays look like they're diverging from each other. They're spreading apart as if they're not ever going to meet each other. And in order to create an image, the rays have to intersect or they have to meet each other. So what we do in a case like this is we say, look, they're not going to meet on the left side of the mirror, on the front side of the mirror, essentially. What if we were to take these rays and extend them on the back side of the mirror? Would they meet? Would anything happen? And so I'm going to do that. But light rays can't travel through glass, all right, a solid medium. So we're going to draw some lines with dots, dotted lines, like we did behind the plane mirror. So I'm going to take this ray, and I'm going to try to get the correct angle. Whoops, I'm going to actually first make this dashed. And I'm using this line originally, how you would put your ruler, to get the exact correct angle. And I'm going to do that. And now as soon as I do that, I see dots on this side. So I'm just going to use flash. I'm going to break that and see if I can select this and get rid of it. So all I've got is the dotted lines at the exact same angle as this ray on that side. All right. I'm going to do the same thing with this ray right here on the exact same angle. I'm extrapolating it back and look, they are meeting. All right. Now, hopefully this dotted line is not too distracting for you. Imagine it's solid here and then dotted behind. Where those rays cross, and the nice thing about flash is where things intersect, you can actually delete the extra stuff. So you can actually see where they come together. You don't have to do that. You don't have to erase the lines. Just where they cross is where the image is going to be formed. I'm going to draw the image now as I have been before. And I'm not being exact. We're just doing it in general. And I happen to have drawn it with dashed lines, but that really doesn't matter. So just draw it like that. And what you can see now about the image, and by the way, before I talk about that, I just want to say you don't draw arrows on this. These aren't real rays going through the mirror. So the rays are here. They bounce this way and that way. You don't draw arrows back there. But what you can see is this image is behind the mirror. So can it really be there? You tell me. It's also larger than the original, all right? And it's upright. So size, larger. Attitude, upright. Location, behind the mirror. Type, virtual. It's not there. It's formed by dotted lines. So do this experiment at home. Take your spoon, start from far away, notice you're upside down, continue to move it up, look at yourself, and you have to get in really, really close, and you'll notice it flips and it gets very large. And that's what's going on with this mirror. Okay? Time out for a second here. Let's get rid of all this stuff and let's have a look at what happens when we move our object behind this concave part of the mirror. And I'm not really worried about F and C on the other side, because really this curved mirror has a focal point right here and a center curvature there. So I'm just moving the object in behind, putting it anywhere. Let's say that you are now behind a convex mirror. Okay, it bends outwards, and you're going to look at where the image is formed. So let's just do this, and we'll talk about some applications in a moment. By the way, I should have told you one thing I forgot to mention, important thing. The use of a concave mirror like this, spoons to look at your reflection. But that's probably not a very practical use. Probably a better use is the makeup mirror. Okay, now this particular makeup mirror that I tried to open and show you before is just a plain mirror. But if you wanted to magnify yourself so that you could properly put on makeup or look at yourself, you know, close up, then a concave mirror like the spoon, if you are inside the focal point right here, okay, looking on the screen there, you will then get an upright, close, sort of magnified virtual image of yourself so that you can see better to put on the makeup or do whatever you need to do, all right? It wouldn't be any good if you were upside down, but you have to be close. If you take the makeup mirror and you put it way over there, that's not going to work. So normally the makeup mirror is up close. I mean, I don't know a lot about makeup, but, you know, it's up close and then it works like that. So concave mirror within the focal point, between the focal point and the vertex, a makeup mirror is a great application. Now, let's look at an application for this. You got the object right there. Let's do our same rules. We're going to draw a line parallel to the principal axis, and we're going to hit the mirror, and then we're going to be in trouble. We're going to say, wait a second. How do I go parallel to the principal axis and through F? If this is a solid mirror, here's what you do. You go ahead and draw your line down through F like that, but you also realize that this is behind the mirror with respect to the object. It was in front of the mirror before, but in this example, it's behind the mirror. And so this is a dotted line. So you make that a dotted line, just like that. Because this is a diverging mirror, not a converging mirror. And that means when rays hit this mirror, they don't go down to the focal point. They bounce off. Like if you were throwing a stone or a tennis ball on a rounded curved surface like that, you hit it, it would bounce up. But on what angle does it go? Is it this angle? Is it this angle or this angle or that angle? How do we know? Well, this is why we do this thing through F. Parallel and through F. And then what you do is you can then say, so the correct angle would be this one. You just use a ruler, follow that. Now I'm a little bit off. I might redo that. It might be off again, but okay. Extend it out a good distance, all right? And once again, this has got to be dotted behind. So I'm just going to see if I can get rid of that selectively. That didn't really work. The best thing to do for me is to go on to another layer. All right, let's do that. Okay. Draw your line like that with your ruler. And then just make sure it's only on that side of the mirror. Okay, now what we're saying is an incident ray will come in here like that, parallel to the principal axis, and it will bounce off like this. This is the reflected ray. We need these arrowheads. But to figure out the angle that it diverges and reflects off, we dot it down through F. Okay, well, we're going to go ahead and we're going to draw another line. And this time, let me come up one more layer. This time, we are going to do the thing where we go through C. So if we hit this mirror exactly 90 degrees, it'll bounce back on itself. But how do we know where that is? Well, let's just go through C. So if you take your ruler and you draw your line down through C as best you can like that, this incident ray right here would be 90 degrees. But it doesn't go right through the mirror as a solid line. It has to be dotted behind the mirror. So I'll go ahead and I'll dot that just like that. And now I need to put on my arrowheads. And yeah, okay. A ray goes in that way and it bounces right back on itself. So that's the incident ray and the reflected ray. But this gives us enough to draw our image because we have the intersection of two rays. So now we can go ahead and do that. So here is where I'm going to draw my image, right down to the principal axis, arrowhead, and this is our image. The head of the arrow is where the lines intersect because they came from the head of the arrow here. So there's our image. And what we see in terms of the salt characteristics for this: size, smaller, attitude, upright, location, behind the mirror. And that leads to type, virtual. Okay, first of all, because it's behind the mirror, it's not really there, all right? And because it's formed by the intersection of dotted lines. Now, if you think of an application of this where the image is smaller than the object, well, this is used in convenience stores, in department stores, in libraries, to be able to see a wide area and to make sure nobody is stealing anything and there's no problems. So for like surveillance or for security, all right? And so go have a look in your library or your convenience store. Look for these sort of curved mirrors. Yes, things will look a little bit warped, all right? But they are upright, all right? And that's helpful for security. It'd be hard to describe to the police. Well, he was walking upside down, okay? Upright, but smaller so you can see a wider area, all right? Now, another thing is, if you've noticed in your automobile, in your car, the side mirrors, right? They often are curved a little bit, and it'll say in fine print, it'll say, object is closer than it appears, all right? Like meaning, when you look, you can see a car there. You're trying to figure out, can I turn? Can I change lanes? You see a car there. The car is not really that small and that far away. It looks smaller in the mirror than the real car, or else you couldn't fit the car in a mirror. So, the mirror is constructed in a way so that you can see the whole car or most of the car, and it looks as if it's further away, but it's actually closer than it appears, because these kind of mirrors make images appear smaller, but at least the right side up. It'd be awfully confusing if you're driving and trucks and cars and planes and trains are upside down. Okay, so the right side up, they are virtual. I mean, the car is not, when you look in the mirror, right, the car's not right there. The car's really back there, although it looks like it's over there in front of you, kind of at the side, but it's really back there, and it's closer than it appears. Okay, now the same kind of thing is going to happen if I move this object. So let's just get rid of all this stuff here. And get rid of that, and let's just do, just another practice thing here where I move the object. I'm just going to move it back, like way back here. All right, so same idea. There's the object, convex mirror. So let's come on in here. I'll try to see if I can speed this up just a tiny bit. All right. Parallel. And then I'm going to draw a line down through F. But this one is going to be dotted because it's going through the mirror, and that can't happen with light. So we make it like that. And then I'm going to come up and I'm going to use the same angle, whoops, to figure out how the light will reflect, just like that. And I'm going to get rid of the solid part on this side. We only want it solid on this side of the mirror as it reflects. Okay? Incident ray, reflected ray, everything's great. We need at least one more ray. We need the rays to intersect. So I'm going to come from, I'll go out to another layer. I'm going to come from here and I'm going to go through C. Okay, as best I can through C. And I know that behind the mirror here, the light can't go through. So this has to be a dotted line. And I know that at this point, the rays are going to come in and go back on themselves, because this, when it goes through C, it's hitting it at 90 degrees. So I've got my incident and reflected ray there, and I'm in good shape, because now I can draw my image, and it's going to be right where those lines intersect, right here. Okay, and you'll notice that the image is, whoops, funny arrow. The image is even smaller because the further away, these mirrors make it look even smaller than that. But again, right side up. So that's the deal with the convex mirror. All right, let's move on to something else then. Let's talk about lenses as well. So I'll clear all this stuff up, including that. And I'm going to grab my object and I'm going to move them back over here. But now when we deal with lenses, we are not looking at F and C. We are looking at F and 2F and a principal axis. And I'm going to get rid of the curved mirror and let's do the biconvex lens. There we go. Okay, this is a lens now. It's not a mirror, so the light can pass straight through the lens. Well, actually not straight through, all right? Because if the lens is made of plastic or glass or some kind of semi-transparent or translucent material, not completely opaque, that the light can go through, light will be bent. Instead of traveling straight and bouncing off of a plane mirror or a curved mirror, light can go through a lens. And when light is bent, we say that it is refracted, not reflected, but refracted. Refraction is the bending of light. All right, and this particular lens is a biconvex lens because it's convex on this side and convex on that side, so it's biconvex. And an imaginary line drawn through the middle here is called the lens axis, and this is the point at which we say light is bent. So we draw a straight line through until it hits that, and then we bend it, and I'll show you that in a second. Also, there's a point right in the middle of the lens that we call the optical center of the lens, okay? So, you'll notice that there's an F and a 2F here. We don't really use C because it's not a sphere or anything, so we say, well, the focal point of this lens and then twice the focal point. And really, because this is a translucent lens and it's biconvex, I could send light from this side over, or from this side, it doesn't matter. So there's sort of like there's a focal point on either side of the lens. And I'll show you something with that. So let's try to figure out what the image characteristics will be like when light travels through a lens. So it's the same kind of rules. Parallel and through F and parallel. And there's one other one that's a modification of going straight through C. And it's going straight through the optical center. So same idea. All right, so imagine here is your object and here is your lens. Light will come parallel, hit the lens axis. Now, it can go through this, so it doesn't bounce outwards. It's going to go through, and it will be bent through F, like this. And these are solid lines. Don't draw this second line here as a dotted line. Light really is going through. But do draw your arrowheads for incident and refracted, not reflected, refracted ray. So there's my first ray. All I need is a second ray that intersects with that one in order to find where my image is. And I can do a couple of different things. I'll do the easy one first, parallel and through F. Well, let's try through F and parallel. So go from the exact same position if you can, down through F to hit the lens axis, and then at that point, light will go off parallel. Now I can see that I need to extend this ray a little bit. I want to bend its trajectory. Okay, so if I do that, I see that the light has intersected. I can now draw my image, and I'll do that in a second. But I'll show you the next rule, and that is going from your object right through the optical center. And if I do this correctly, it will also intersect at that point. So I could use any two of these rays. I don't have to use three. But anyways, now I'm going to draw my image, and this is where it is, right up to the principal axis, just as my object was sitting on the principal axis. And because the light was coming from the tip of the arrowhead, this is the arrowhead right here. So this is my image. All right. You'll notice all of these are solid lines, and the fact that I really should have arrow here, arrow here, arrow here, and arrow here. All right. These are incident rays. These are refracted, and they all need to have the proper arrows on them. Okay. Anyways, here is my image, and it's formed on the other side of the lens. So let's go through the SALT characteristics of the image. Size, it is larger. Attitude, it is inverted. Location, it is on the other side of the lens, behind the lens, you could say. Type, well, you tell me. Solid lines, this is a real image. Okay. So in other words, I mean, if you were looking on this side, if you were over here and this was a glowing thing, all right, and you were looking through the lens, you could see that thing. All right, let's go on and let's move that object to another position. All right, here's an interesting one. Let's move the object right to the F position. Okay, as best I can get it on there, and let's try this. Parallel through F. I can't go through F and parallel. That doesn't work because I'm standing on F. So I'm going to go through the optical center. Now, if you've drawn this correctly, you will note that these rays appear, let me do this first. Incident rays, refracted, not reflected, refracted rays, right? These rays appear to be parallel to each other. If I was to extrapolate these backwards, as I will in the next example, they would also be parallel. Because what doesn't work on one side of the lens or the mirror, you often try on the other to see if they will meet. They will not meet. And because of this, no clear image is formed. So you don't do the SALT characteristics. You just say no clear image. Because the rays are parallel. In order to form a sharp image, they need to intersect. So this is a strange situation where you would think the object is at the focal point. You know, it sounds like the exact right spot for the best image. It's actually not. It's the reverse of that, all right? And this is how you prove it. It just doesn't work at that point. Now, let me show you something cool, though. If we take this object and move it within the focal length of this lens, the focal length being the distance from the optical center to the focal point, if we put the object right there and then we try to figure out the image characteristics, let's do that. Let's draw the ray diagram. Parallel to the principal axis, hitting the lens axis, and then down through F, solid line, not dotted line, incident, refracted. Let's do another one. I'm not going to go through F and go backwards. I want to go this way through. I want to see if the rays join. So I'm going to go through the optical center. And I'm going to get this. Okay, I'm going to put on, whoops, incident ray, arrowhead, in other words, refracted. Now, notice that these rays look like they are separating from each other, right? They're getting further apart. They are diverging. if it's diverging on one end, chances are they're going to meet on the other. So in this case, we are going to try dotting the rays backwards. So let's go ahead and get this set up. Go up to, yep, another, come back to here, just so I can get my angle right. I'm going to start right there. And I'm just going to go back pretty far. And I am going to make this a dotted line. And the reason is light is not bouncing off this lens and going backwards. All right. We are doing this to extrapolate the rays backwards. I'm just trying to get rid of this part here. And see if the rays will meet, you know, in front of the lens. Okay. So let's do the same thing over here. And I will just take it from there and I will bring it on the right angle. And as you can see, the rays do meet back here. So always try that. If the rays look like they're diverging, bring them back and dot the rays if necessary to see if they're going to meet. And they do meet. And just to see more clearly where they meet, I can just clear that up. That's the point they met. And so I can now draw my image right here. There it is. This is the top of the image right there because it came from here. And now I can do the salt characteristics when my object is within the focal point of that lens. All right. And the salt characteristics are size, larger, attitude, upright, location in front of the lens, and type, you tell me, dotted lines, virtual. It's not really there. I mean, how could it be, right? Here's the object. The image is back there. Right? It's like it's behind me, okay? Someone's watching me. And it's a big guy, too. This is the concept of the magnifying glass. Imagine this was a magnifying glass that you're holding. You know the way when you want to look at something under the magnifying glass, you get up nice and close to it, right? You're having a real close look at that insect or whatever it is. And it's magnified. It's bigger and it's magnified. All right? So that's how that would work. Okay, we're going to clear all this up and let's move to another kind of lens, okay? Because even if I was to take this and move it on the other side, I would just be repeating myself. The rays would be coming in from the, you know, right to the left instead of the left to the right. So it's the same idea, okay? So let's instead, in fact, I could keep it here. I could keep the object there for the next type of lens. Let's do that. This kind of lens, biconcave. Goes in on one side, in on the other side. This is called a biconcave lens. All right, still got a lens axis, still got a principal axis, and the optical center. F and 2F. I can do it from either side because it's translucent, the light will go through. So let's try it from that side just to show you. All right, so let's draw a ray diagram and figure out the image characteristics. I'm going to draw parallel to the principal axis and hit the lens axis. The light will refract through and go down through F, just like that. I will draw my incident ray arrowhead and my refracted ray. And now we need at least one more ray that will meet. Now, I'm not going to go backwards, the rays will never meet, so I'm going to go through the optical center. So here I go, down through the optical center, like this. And the rays aren't meeting, okay? It looks a little bit like they're spreading out. So let me try. If they're spreading out on one side, they might be going straight on the other. So let me try going backwards then. Extrapolate backwards at the exact same angle. Let's see if they're going to do anything. This, of course, is a dotted line because the light is not going backwards. Not really. It shouldn't be. So I am going to make it just go backwards from this point. Okay. I extrapolated that one backwards. Let me try this one as well. I'll try it from there to go backwards. And oh, we're looking good at that point, right? I'm going to get rid of the dotted line on this side just because this is the way I'm drawing it in Flash. You'd be using your pencil and your ruler. We extrapolated backwards because these lines were not going to meet. We draw our arrows on here. Incident ray goes right through. Refracted ray goes right through. We do not draw arrowheads on these. All right, these are just used to figure out where the rays intersect. and right about there. Okay, I can now draw my image right about here. All right. Oh, I did in dotted lines, so that's okay. No problem at all. Image is right there. It's actually kind of appropriate that I did it that way because this is a virtual image. All right. Here's our object. This is a virtual image that is larger, located in front of the lens on the same size, same side, and it is upright. All right. So if we really wanted to, we could try one more example. Let's just move the object to another position and see how things change, if things change. Let's just go in between here and see what happens, following the same rules. Parallel, straight through F, solid lines. Now at this point, I can do a couple of different things. I can do whatever I want. I often like going through the optical center, so let's try that. Straight through the optical center, and look what happens. All right, they do intersect there. Okay, so it looks as if I am going to be drawing my image right about there, like this. All right. So when the object is in this position, size larger, attitude inverted, location behind the lens, type real. Good. Let's do one more. Let's really bring out the object real far. Last one. Object way out there. Let's see what's going to happen. Same rules are going to apply. Parallel and through F. Incident, refracted. Okay. What do I want to do? Optical center? Why not? Just like that. Same kind of concept. Always the same. Just follow the steps and you're set. There it is. Boom. All right. Well, in this case, smaller, inverted, behind lens, real image. All right. So that's a couple of tips on how to do these ray diagrams. I know students, this is for grade 10, of course. Students often find it frustrating and hard to do. It's really not that hard to do. And I hope this will just serve as a review for you guys to practice doing these. And I wish you luck in your endeavors. Okay, take care.